Yes, sorry, just give me a second while I start the screen share.
Hello everyone, this is Germán Vidal, and today I'm going to present our recent work on improving Coder, which is a causal, consistent, reversible debugger for Erlang. This is a joint work with my PhD student Juanjo. We both belong to the Valencian Research Institute for Artificial Intelligence at the Technical University of Valencia, Spain. So let me first briefly introduce Coder. As I said before, this is a causal, consistent, and reversible debugger for Erlang. Well, I think that the notion of reversible debugging is very intuitive. So in our debugger, you can explore a computation in the standard forward direction, and if at some point you see some incorrect behavior, then you can start undoing the steps. That is, you can start going in the backwards direction and try to find what is the cause or the source of this error. Okay, so I think this is a very intuitive idea. But extending this idea to the context of a concurrent language is not so easy. So in particular, let us consider some typical client-server application, okay, in which we have a number of clients, say C1, C2, and C3, that perform mostly independent actions, okay? So the actions of C1 has nothing to do with the actions of C2, etc. So in this context, if we consider a standard or forward computation, and at some point we see that one of the clients, say C2, performs some incorrect action, or we observe some incorrect behavior for this client, we don't want to undo all the actions of this forward computation, because many of these actions performed by C1 and C3 are typically completely independent of the actions of C2 and completely independent of the error or the incorrect behavior that we observe. Therefore, here we use the notion of causal consistent reversibility introduced by Danos and Krivin in 2004, which means that we don't need to undo all the actions in exactly the same order, but every possible reversible computation is correct, is acceptable, as long as it's causal consistent. And causal consistent means that we cannot undo any action until all the actions that depend on this one have been previously undone. Okay? I think this is quite an intuitive idea. It means that we cannot undo the sending of a message until the reception of this message has been undone, or we cannot undo the spawning of a new process until all the actions of this process have been undone. Therefore, in the context of the application that I was mentioning before, in this particular computation, we will ask the debugger to only undo the actions of C2 and those actions that depend on the actions of C2. But every other unrelated action will not be considered. And that's very good from the programmer point of view, because one can focus on the actions of the process that produce some incorrect behavior. Okay. So as for the motivation of this work, initially, some 5 years ago, we considered Core Erlang for our developments. Core Erlang is the intermediate representation used by by the compiler, by the Erlang compiler. It's similar to Core Haskell in the case of the Haskell of the functional language Haskell. So we consider Core Erlang both for defining the standard and the reversible semantics, that is for our theoretical developments, and also for implementing our debugging tool. And the reason is quite obvious, because the syntax of Core Erlang is simpler than the syntax of the source language. Unfortunately, later we discovered that that was not such a great idea from the point of view of the programmer. And the reason is quite obvious. I mean, this is a source Erlang program, and this is the corresponding translation to Core Erlang. Well, as you can see, there are some similarities, but also many differences. So we are introducing a number of constructions that are not present in the original code. So basically, instead of equations we have just one big lambda expression. We introduce a number of let expressions that you cannot see in the original code. Applications are explicit, etc., etc. Okay, there are some additional default cases. So that means that if the programmer writes the code in the topmost part of the slide, and we show this code in our debugger, well, this is going to be very confusing for the programmer. And this is even worse if we consider a large application. Okay. Therefore, the motivation for this work, was to move from core Erlang to Erlang, both at the theoretical and at the implementation level. So, in particular, we have redefined all the semantics involved in our approach, which is the standard semantics, logging semantics. This is a slightly extended version of the standard semantics in which we produce a log of a computation. And this semantics is used in order to define a replay approach to debugging, in which the forward computation is not driven by the user but driven by a log that is computed from some previous execution. And then, of course, the reversible semantics and what we call a control semantics that, well, I will explain what is the role of this control semantics later. So in doing so, we have also considered a number of extensions. Okay, in particular, we have added some additional features that were not considered before, like higher order functions, conditional sequences, etc. We have integrated the two previous approaches. User-driven means that it's the user that decides what is the next action when following a computation in the forward direction. So essentially, the user decides what is the process that should perform the next action. And a replay approach that is based on using a log, as I was mentioning before. So we have integrated now these two approaches. And finally, we have also redesigned the user interface of our debugger, and well, hopefully now it's closer to, it's more intuitive for the programmer because it's closer to the interface of the standard debugger of Erlang. Okay. Now let me show you some technical details of our approach. As I said before, we consider the functional and concurrent programming language Erlang. Concurrency in this language is based on message passing. Okay, so at runtime we have a number of processes that can only interact through message sending and receiving. There's no shared memory. We also consider that communication is asynchronous. Each process has a unique identifier that we call the bit of the process, together with a local queue, okay, which is a sort of mailbox, where messages delivered to this process are stored until they are consumed by a receive statement. And well, we introduced this notion of system, which is essentially a representation of the state of a running application. Okay, so it includes the current state of each process together with a representation of the network. I will show you some details later. So I'm not going to describe the sequential component of the language because it's a typical eager functional language. So let me just focus on the main concurrency features. Here we have spawn, which is a built-in function that creates a new process as a side effect and returns the fresh bit of the new process. Okay. Self, it's a very simple built-in function that returns the bit of the current process. This expression with this exclamation mark, with this operator represented by an exclamation mark, is used to send a message. So the first argument is the bit of the target process, and the second argument is the value, the message that we want to send to this process. Okay. So this message will eventually be stored in the local mailbox of the target process, and the evaluation of this expression returns the value that we are sending. And finally, we have a receive expression. Syntactically, it's very similar to a case expression, but in this case, we try to find a message in the local mailbox that matches any of the patterns in the branches of this receive expression. I will show you an example in the next slide. Okay, and when there's no such a message, then computation suspends. Okay, So let me show you a very simple example in Erlang. This is a sort of minimal client server in Erlang. Here we assume that the initial process is the client, okay, and it starts with a call to function main, and main performs two actions. The first one is spawn, so we create a new process. Let's call this new process the server, and this new process will evaluate this with the start by evaluating this expression, a call to function server with an empty list as argument, which somehow represents the initial state of the server, okay. So spawns returns the PID of the new process, the server, and then we pass this value to a call to function client. Okay, spawn is asynchronous, which means that we create a new process as a side effect, but we continue with the call to function client. Well, you can see function client here. The definition is, I think, very intuitive. It essentially sends three messages to the server: add paper, add pencil, and self take. Okay, the first two messages are, well, quite simple, and in the last message you can see that we have a first argument here in this tuple that is a call to function self, and this is a typical construction when we want to get an answer back from the server. Okay, so we send our own PID. This is what the self returns. Okay, so this construction is essentially a simulation of asynchronous communication, because we send a message and we keep waiting in this receive until an answer is sent back from the server. Okay, and if you look at the server, it's essentially an endless loop, okay, that is waiting for two different kinds of requests. So it could be add item or take. If the request is the message that arrives to the server is of the form add item, then we just add the new item to the list, and we call recursively to function server with the new updated list. Okay, and if the message is take, then we use the first argument, which is the PID of the client, okay, to send an answer back to the client. In this case, we send the element on top of the list, okay, and then again we have a recursive call to function server with the remaining elements. So this is a very simple client server in Erlang. Okay, so this is the syntax of the language that we consider in this work. Okay, well, you can find the details in the paper. So let me just mention what are the main differences with respect to our previous approaches to reversible debugging, where we consider core Erlang instead. So on the one hand, we have sequences. A sequence have this form, okay, and evaluation proceeds from left to right. Okay, so we evaluate E1, then we evaluate E2, etc. And the complete sequence is reduced to the valuation of En. Okay, and we also have pattern matching equations that have this form. In this case, we first evaluate the expression in the right hand side, E, to some value, and then we perform pattern matching between the pattern P in the left hand side and this value V. Okay. Another novelty are conditionals or if clauses, which are sort of a special case of a case expression. Okay, and finally we have higher order functions that were not considered before. Okay, this is how we formalize the notions of process and system. A process is a tuple of this form, where the first component is the PID of the process, the second component is the current environment, which we represent by means of a variable substitution. The next component is the expression to be reduced, and we often denote it in these ways, where C is a context and R is the next regex to be reduced according to typical eager functional semantics. And the last component is a stack that we represent by means of a list. So a system is then formalized in this way, is a pair gamma pi, where gamma is a multiset of triples of this form. Okay, so basically a multiset of messages that we represent by means of a triple with the PIDs of the sender and the target processes, and then the message, okay, the value of the message. And this gamma is called the global mailbox, okay, and it models both the network and the local queues of the processes. Okay, observe that we don't have a component to represent the local queue in each process, but this is part of gamma. This is represented by gamma 2. And then the second component, pi, is a pool of processes where processes are composed using this operator, okay, which we consider it's a commutative and associative operator, and therefore an expression like this one is used to denote an arbitrary process P in a system. Okay, before moving on, let me say a few words about the design of word semantics. So the semantics is defined in a hierarchical way, so we have different layers. In the first layer we define the semantics of expressions, both sequential and concurrent expressions, and on top of that we have a second layer where we define the semantics of systems, okay? And the nice thing of this design is that in order to introduce a new semantics, say a login semantics or a reversible semantics, we don't need to change everything. Okay, so we can produce a login semantics by only replacing the rules that define the semantics of systems, but we don't need to change this part. Okay, well, a login semantics is essentially a standard semantics that produces a log of the computation as a side effect that is then used by the replay debugger, okay, in order to replay a particular execution. And similarly, we can define a reversible semantics by only changing this layer, but we don't need to change anything in this part of the semantics. Okay. Well, the reversible semantics is in principle non-deterministic, which is what we call an uncontrolled reversible semantics. And in our debugger, we have one more layer, which is what we call this control semantics, which is where we have the rules that takes the request from the user, requests like go forward until the sending of this message, or go backwards until the spawn of this process, and then takes this information and drives everything in this semantics. Okay, let me show you a hint of the different semantics that we define in this work. Well, and particularly I will focus on the differences with respect to the previous work. So regarding the standard semantics and the evaluation of sequential expressions, the main difference is that now we need to introduce stacks. Okay, that was not needed before. And the reason to introduce stacks is that now we consider sequences. Okay, so let me explain the point with an example. Consider, for instance, an expression like this one, case some function call of and a number of branches. Well, this is a legal expression. But if we perform one unfolding step, okay, the next expression to be reduced is this call, we might get a sequence of expressions. I mean, the right-hand side of function f may contain a sequence of different expressions, okay? However, this is not a legal expression anymore, okay? So in our small step semantics, this intermediate expression where we have case and a sequence of expressions is not a legal expression, okay? It's not legal. Because in the Erlang syntax, the argument of a case expression must be a single expression. Okay. Therefore, our solution is to move the context, this part in this case, to the stack. Okay. So that we can now perform the unfolding of the function call, and even if we get a sequence, that's not a problem because this is the only expression that we have in our process, and we keep reducing this sequence until we get a value, and once we get a value we can just get back the context and resume computation. Okay, so this is a well, more or less standard strategy, and we have to do the same also for case expressions, because we have a similar situation, because a case expression can also be reduced to a sequence of expressions, and actually also for conditionals, right? So you can find more details in the paper about that. And well, regarding the evaluation of concurrent expressions, there are just some minor changes with respect to previous approaches. For instance, this is how we evaluate, how we reduce a call to function spawn. Okay, so we had to do that at two levels, as I mentioned before. So we have two layers, one at the level of expressions and one at the level of systems. So we have two rules for every concurrent feature. So for a spawn, we cannot do anything at this level, okay, because I mean we need to see the complete system. Therefore, what we do is to label the step with all the required information. We also replace the call to spawn. We reduce the call to spawn to a fresh variable, kappa, sort of future, okay. And with all this information, it's the next layer of the semantics that the rule that reduces systems, okay, where everything is visible, So at this level, we can perform the corresponding side effect, which is adding a new process, and we can also bind this variable kappa to the corresponding PID of the new process. Okay, so these two rules cooperate in this way. And we have similar pairs of rules for sending a message, receiving a message, etc. Okay. As for the reversible semantics, the main difference with the standard semantics in our previous approach is that we introduced two new components to each process, omega, which is the log of the process, okay, and h, which is what we call the history. And well, this is essentially a list of items with enough information in order to undo each computation step of a derivation, okay. And well, the definition of a system is essentially the same. So in this work, we have slightly changed these definitions. Okay, so now a process is defined in this way. We only have a history, but we don't have a log. So the logs are now a global parameter of a system. Okay, and this change was required in order to integrate the two approaches to debugging, to reversible debugging. The user-driven approach, where it's the user that decides what is the next action in a forward computation, and the replay approach to debugging, where the next action is determined by the log of a previous computation. Okay, so well, this is how it looks like. So we have now two rules for every concurrent feature. So for receive, we have one rule where the log is empty, and therefore we have to select any arbitrary message from gamma. Okay, so this is an arbitrary message in gamma. And we have a second rule where the log is not empty. So if the current log says that we have to receive the message with this identifier, with this label L, this is the only message that we can receive. And if this message is not in gamma, we cannot perform this step. Okay. So we have, as you can see, we move information from the log to the history. And this is the opposite, the rule in the opposite direction. So when we go backwards, we have to move information from the history to the log. Okay, well, you can find the details in the paper. I just want to mention that we have integrated both approaches, user-driven debugging and replay debugging. Okay, and then the main change, as I mentioned before, is that now the logs must be a global parameter of the system. Okay. Well, finally, we have the control semantics. And as I said before, well, at this level, the user can introduce a number of requests like go forward or backwards one step, or go forward up to the sending of a given message, or go backwards up to the sending of a given message, etc., etc. And well, the steps must be causal consistent. So one step forward might imply some more steps in other parts of the system, but this is transparent for the user. And well, you can find the formalization of these semantics in the paper. Okay. Let me conclude by mentioning several possibilities for future work. So we would like to add support for more Erlang features. Okay. Well, ideally, we would like to cover the complete language at some point. Secondly, and this is quite challenging, we would like to deal with distributed applications in which the source code of some of the modules is not available, okay, and therefore we cannot instrument these modules. And well, this is something that we need to do in the current approach. Next, we would like to implement a new, more efficient version of the tracer. The tracer is the tool that instruments the source code of a program, so that its execution produces a log as a side effect of the execution. Okay. We would also like to port different extensions that were developed for the old version of the debugger to the new one, and so forth. Okay, and thanks for your attention.
Thanks for this very interesting presentation, and the floor is open for questions. Please just voice your question when. Go ahead.
Hi. That was really interesting. I'd like to give it a go. We teach Erlang here, so it could be interesting to try that out with students. One thing I was wondering about is is timeouts. You didn't mention timeouts in selective receives. Is that something that's on the sort of to-do list, or is there a way of already integrating that into the debugger?
This is quite an interesting feature, but it's still featureware. So we are not considering timeouts. So you need to completely different semantics, including time and well, anyway. So we can deal with applications, including these timeouts, in some partly, because we instrument the source code and we run the program in the standard interpreter, in the standard compiler, in the standard environment. And what we get is a log of the computation. Therefore, we are going to mimic more or less the same behavior in our debugger. Yeah. So our semantics does not include time, but we can deal with programs that use this feature because the standard environment accepts this kind of feature.
Right.
But of course, it would be better to be able to model time in our semantics and therefore to be able to extract some more interesting properties from that.
Well, I was thinking there's also this funny trick you can do with the after timeouts where you can clear your mailbox by doing receive with after 0. And it does this sort of thing where it like garbage collects your mailbox. I guess that's maybe not a problem for you, saying, given what you just said. But yeah, I started thinking about all these slightly strange things you can do with the time system.
Actually, this is something that you would get by executing the program and then getting the log. You will get exactly the same behavior.
Yeah, great.
Thank you.
Any other questions? I would have a question related to the possibility of moving this semantics and then possibly the implementation as well to other languages that have adopted Erlang's very popular concurrency model. One of them that I know closely is, of course, SWI Prolog, where we have a very, very similar message passing between threads, and they have also engines now for asynchronous communication, or a language like Scala, which also has adopted Erlang's model. And some of those would be also benefiting from reversibility. Let's say in Prolog, that's a very natural feature. So if you had a semantics that's reversible, do you think that it would be very hard to cover some of those languages that have a different surface syntax, but essentially the same concurrency model?
That's a good point, and I'm happy you asked this question because the truth is that, yes, I think that the model is very general. I mean, we basically need these 4 basic concurrency features that I mentioned, the fact that you can spawn a new project, send a message, receive a message, and you can find these features in almost every message passing concurrent language, and therefore adapting all these causal consistent reversible debugging model would not be difficult. Actually, I have already presented the first debugger for sequential sweep Prolog, and I think it could be extended with these features if you consider the concurrency features of the concurrent extension of the language. So that's a promising approach for future work, right?
Well, thank you. Let's see if we have time for maybe one more short question. If not, let's thank the speaker. And we are ready to move to the next talk, the final talk of this session, declarative debugging of XML queries. And the talk is by Jesus Almendros Jimenez from Universidad of Almeria and Antonio Becerra Teron. I'm assuming the first author might be the speaker. Please go ahead.
Yes, I am. Yeah. Hello. My name is Jesus Almendros, and I'm going to talk about declarative debugging of XML queries. This work has been developed at the University of Almeria together with my colleague Antonio Becerra. First, I will present the main element of declarative debugging. Second, I will explain how to adapt declarative debugging to the X-query case. In particular, I will show you how to build the debugging tree and what type of question users have to answer. A key point of the proposed approach is that query answer can be classified into partial incomplete and partial incorrect answer. Also, I will introduce new debugging strategy specifically designed for X-query. I will give you some details about the implementation, in particular about the developed web tool, and I will finish presenting some conclusion and future work. First, proposal for logic programming, declarative debugging has been used in many other programming languages, like Java and Haskell. This is not the first time in which declarative debugging has been used in database programming languages, because it has been adapted already for SQL and Datalog. Basically, declarative debugging builds a debugging tree in which function calls and nodes and child-parent relationships describe code structure. Such a debugging tree is built from Abram answer in such a way that it represents his trace. The user or the debugger answer questions about the validity of the results in each node. A buggy node is found when children are valid and the node is invalid. Buggy nodes correspond to buggy codes. Several strategies have been studied for the traversal of the debugging tree in order to reduce debugging time. In essence, less question means fast debugging time. The idea is to reorder questions, giving more purity to some question or avoiding question already done. The novelty of our approach is that the debugging tree includes function calls and XPath expression. XPath expression are central in X-query. XPath expression serve to retrieve branches of XML trees. Most of X-query programming error come from incorrect XPath expression, typically due to missing XML tags, overabundant XML tags, or brown Boolean condition. According to this, we have defined due strategies which take into account that the debugging tree have two kinds of nodes. Since X-query program work with sequence of XML trees, the definition of broad programs has to take into account that answer can be incorrect, incomplete, but also partially incorrect or partially incomplete. Here, we can see how the debugging tree is built. The root is the query, and each path or function call generates a child. When a node is a function, it may have children built from the function call and path of his code. The aspect of the debugging tree is something like this, in which each node has a query, path, or function call, as well as the input and output XML trees. In the general case, the input and the output can be a forest of XML trees. Now the user has to answer questions about each node. The question is whether the path of the function can take a given input and return a given output. The answer can be yes or no. The debugging process ends when all the children of a non-valid node are valid. That is, the answer to the node has been negative but positive for all the children. It means that the code of the node is incorrect. Such nodes are called buggy, and the code or buggy nodes is incorrect. However, the concept of broad program has to be well defined. A query can return a tree or a forest. So the answer can be correct, but also partially incorrect or partially incomplete. Partially incorrect means that at least one of the branches is incorrect. Partially incomplete means that at least one of the branches is missing. If we extend this concept to forests of Ecklem's trees, we have correct forest, incomplete forest, incorrect forest, and also partially incorrect and incomplete ones. Path and the main cause of incorrect and incomplete answer. This is an example. Here, a list of proceeding books should be retrieved by a query. However, one of the books is incorrect in the first case, or is not found in the second one. Here, there is an example of error in a query. This is the most frequent error. A path is incorrect. Some of the tasks is missing or incorrect. Let us see now the case of a Brown Boolean condition. Brown Boolean condition can produce few answers, in particular none, or abundant answer. Here, the error comes from Brown combination of paths and Boolean condition. This is another error which comes from a Brown arithmetic expression. In this case, a Brown task in the path expression leads to non-empty answer, but it is incorrect. Now, we can see the aspect of question in the debugger. Here, a question about a path in a XML tree is asked. Here, there is a question about the result of a function. And here, we have a question about a path expression about an input document. Let us see now about the strategy. A naive strategy traverses the debugging tree without reordering. That is, Q, Q1, Q2, Q3, and so on. Here, green nodes are path and blue nodes are functions. A first strategy is to ask about path first, because they are frequently the cause of the error. Here, green nodes are retrieved first. Another strategy is to delay paths and analyze function calls first. That is, blue node first and red node later. Another strategy is to look for empty paths. With this aim, the size of the result is taken into account, and nodes are sorted with regard to the site. So, empty paths are first found. We have proposed more strategy. Some of them are specifically designed for X query, but some others are typical of declarative debugging. This is the case of heaviest node first, or divide and query. And we have analyzed the degree of success of the proposed strategy. The degree of success is analyzed in terms of the number of questions. With regard to the implementation, we have implemented the debugger in X query itself. It permits that the debugging tree is a XML tree, and the result of the query are subtrees of the debugging tree. One of the advantages of our implementation is that XQuery is a higher order programming language, and we have implemented the traversal function as a higher function. The sorting of children is given by a sorting function, and the user can define his own strategies. For instance, this is the code of one of the proposed strategies. Here, a couple of slides about the bot tool. User experience is improved by using a grid to show the debugging questions. Also, the grid is used for visualizing input and output XML trees. Let us finish Let us finish by concluding that a new technique for X-query debugging has been presented. Specific elements of declarative debugging has been designed for the X-query case. Our experience with the debugger is fine, but we believe that we can improve the debugging process. Some pending questions are, for instance, trusting, make possible answer that a function can be assumed to be correct. The second question, or the second topic to be there is to allow I don't know answer, to make possible answer that something is not known, or the handling of exception and non-termination to save space and improve performance, and finally to take into account sub-tree analysis for partially incorrect or incomplete answer. And that's all. Thank you for your attention.
Thanks for the talk. We have time for questions. I have a question. It's very interesting to debug query languages like Xquery, and I know that an alternative to XML, especially when dealing with programming language data exchanges, is JSON, and I know that Xquery 3.x is able to handle JSON as well as XML. Did you think about adapting that, fine-tuning it also to cover JSON? Because that would be very useful for interoperation between programs written in different languages, in particular web servers and clients.
Yes, I think it's a good question. In my opinion, it's possible to adapt to JSON because basically Xquery represent JSON documents as XML documents. There are some difference between the normal standard, the standard aspect of XML documents with regard to JSON documents, but basically JSON documents are XML documents. But I think in any case that you should modify the implementation in some sense that in order to cover the special structure of JSON documents, in order to provide better questions about JSON, more suitable for JSON documents, because the structure is similar but not the same.
Mm-hmm. Thank you. Let's see if we have any other questions. If not, let's thank the speaker. And I believe this concludes our session.
Yes, that's right. Yeah.
So thanks for all who participated to the session, and I guess we have a coffee break coming soon. So
and the next session will be well, we ended a bit sooner, I think.
I think we've ended late because we had several technical issues. So.
Okay, yeah.
So I think we're in. No, actually, I don't know what's going on anymore. Where are we? Oh no, we did finish sooner.
No.
It's getting my head around the time zones. Okay, so we can have a little bit more of a break then and relax, stretch our legs. We'll be back soon. We'll be back at the hour.
to give a talk about synchronous message passing with priority. Priority is crucial in different contexts. Our long-term goal is to develop a functional programming language for real-time systems. That system software can be an airplane controller or autonomous vehicles or some other online.
In case anyone's watching the live stream, we're just testing. But Jose, I can't actually see that video now.
Concurrent ML, or for CML. CML is a synchronous message passing language. It provides a robust
So is it coffee break yet?
Yes.
Yeah.
Yeah, sorry, we're doing some test. It's coffee break.
primitive tips for programmers to construct a multi-threaded code under the message passing context. And the challenge here is we want to know the definition of priority in a synchronous message passing language. And to help you better understand this challenge, let's start to look at some CML primitives and look and see what it provides. And begin, we have an example of the communication in message passing under the CML context. This is a diagram. We use a notation. The black line stands for a running thread, and the green line stands for a waiting thread. Red line stands for a blocking thread. In this example, we have two threads, T1 and T2. At the beginning, T1 is up and running. It executes until it performs a send action. The send action. My name is Cheng Zhang. Today, I'm going to give a talk about synchronous message passing with priority. Priority is crucial in different contexts. Our long-term goal is to develop a functional programming language for real-time systems. That system software can be a airplane controller for autonomous vehicles or some other online streaming services. And our starting point will be using concurrent ML. So for CML, CML is a synchronous message passing language. It provides a robust primitive tips for programmers to construct a multi-threaded code.
Yeah, that seemed to work fine.
Yeah, I think that as soon as I switch the window, it will break. So I'll try to connect with my phone on Slack, and then I can have two devices and not touch the computer.
Yeah, that's why I've got this. Okay, great. See you in a bit. Hello. So 4 minutes to start. And according to my notes, the speakers are Cheng and Chuang that I see. You want to try the microphone or the camera?
Yes, I'm here. Can you hear me?
Yeah, I can hear.
Okay.
Good. So we will collect the question. And for the second paper is Bhargav. I hope to pronounce correctly, but please fix my pronunciation. Bhargav Shiv Kumar.
Yeah, you got that right, Mario. I'm here too.
Okay, thank you. I'm very bad with pronunciation in general.
No, you were spot on.
Good. So your microphone is working. Thanks.
Yes.
And what about the third paper? It's a short paper. And according to my notes, the speaker should be Reed Hohei or Red Hohei, but I don't see in the list. So maybe we have a missing speaker. They might appear soon. At least they're. I have seen Reed around. They have been in sessions earlier, so that they are here at they're here at PADL somewhere. Yeah, they're probably still having a coffee. Okay, fantastic. Okay, so I'm confident that it's going smooth with the video. Let me check if the live stream is still working. Yeah, why not? We have time, so better to check now. So the short paper is also 30 minutes slot. Yeah. Okay, good. Yeah, everything seems working. Yeah, let's see. And then after this session, Jose, you're gonna close out because this will be the last session, right? Okay, yeah, that's the last session. Okay, so yeah, and you will greet everyone, I guess. Yeah, very good. Let's see for how long my kids will keep silent. I'm very curious. That's why I came to my office.
What can go wrong? I mean,
everything. Yeah, usually they prefer to stay with the mom, but just when I cannot really give time to them, then they want to stay with me. It's it's Murphy law, something like this. Yeah, I've had some pretty interesting things happen during teaching with my kids. It's been quite funny. The students don't mind. They kind of like it. Good. So questions usually come from many directions, from the chat there in this cloud. Okay, so I try to monitor everything. Let's see. Yeah, I think most people I think mostly we've just been unmuting ourselves. People can unmute themselves at the end. I think it's easier. So I suggest. I mean, we are a small group, so I think the easiest way to do a question is to unmute and ask. Yeah. I think more people will sort of join after the first few minutes. We've been seeing that people sort of start coming in a little bit later on.
So should we wait another minute or we start? What do you think?
We can wait 1 more minute.
Yeah, okay.
I'll let Jose take control. I think he's now got...
Read.
You're doing the video.
So read or read, what's the pronunciation?
It's read.
Read. Okay.
Yes.
Nice. Read Hohei, while the tool is named Samati.
It's mostly arbitrary, but it's a random Greek god that is associated with beaches. So like current like flow, or the ocean like flows in and flows out, and there's flows in the language.
But the pronunciation is Samati.
Samati, yeah.
Samati. Okay. Good, good.
Yeah. And it's not used for anything else as far as I can tell. So
I'm curious to listen to the talk. Okay, so we have all the speakers, so I think we can start this closing session. So it's foundation and programming concept at work. So we expect to have practical stuff here, guys. So we have 3 talks. As usual, we are going to play some video for around 24 minutes. Then we have time for around 5 minutes of question. Please attend all the talks, keep notes, and if you have questions at the end, the easiest way is that you unmute yourself and do the question. And if you have really problem with the microphone, you can write in the chat of Clouder, and I will try to handle question in this way as well. Good. So the first talk is entitled Synchronous Message Passing with Priority. And the speaker is Cheng and Chuan from University at Buffalo. And I think we can start to listen to the talk.
Hello, everyone. My name is Cheng and Chuan. Today, I'm going to give a talk about synchronous message passing with priority. Priority is crucial in different contexts. Our long-term goal is to develop a functional programming language for real-time systems. That system software can be an airplane controller or autonomous vehicles or some other online streaming services. And our starting point will be using concurrent ML, or for CML. CML is a synchronous message passing language. It provides a robust primitive tips for programmers to construct a multi-threaded code under the message passing context. And the challenge here is we want to know the definition of priority in a synchronous message passing language. And to help you better understand this challenge, let's start to look at some CML primitives and see what it provides. And begin, we have an example of the communication in message passing under the CML context. This is a diagram. We use a notation. The black line stands for a running thread, and the green line stands for a waiting thread. Red line stands for a blocking thread. In this example, we have 2 threads, T1 and T2. At the beginning, T1 is up and running. It executes until it performs a send action. The send action will send the value V to channel C. After T1 performs the send action, it blocks. And so once T1 blocks, T2 has a chance to up and running. As we can see, T1 is blocked and T2 runs. It stops until it performs a receive action. The receive actions here is to receive from channel C. Note that this is a pairing of send and receive, both try to act on a channel C, so we can pair them together. Once we pairing them together, and the value will be sending from T1 to T2. Now, the T1, after the communication, T1 gets unblocked, it has a chance to be scheduled, and T1 can be scheduled. Once it is scheduled, T1 will be allowed to get up and running again. And the main observation in this example is, since synchronous message passing is synchronous and threads blocked, and so the communication patterns can have a direct impact on which threads get executed. After we understand the example, let's look at some events, first-class events, or sometimes we call protocols. CML provides first-class events. These events are the description of communication protocols. And protocols are executed when those events is synchronized by a thread. Note that the events is a first-class value, so it doesn't have to synchronize. A thread can construct an event and send that event to other thread before the synchronization. The send and receive, what we have seen so far, is basically a synchronization on a send event and receive event. It can be expressed in terms of this sync on send CV and sync on receive EVT on the channel C respectively. So these are the first class event. In CML, let's consider adding a priority to this messaging passing. We started to adding this priority with a traditional approach, which is associate the priority levels with a thread. And let's look at how it goes when we adopting this approach in a CML. First, in this example, we have 3 threads. The first thread is TH. The H here stands for high. It's a high priority thread, and we have 2 low priority threads in this case. And at first, of course, the high priority threads has a chance to be the first to up and running, to be the first to run, and when it runs, it construct a send event, and the send event is basically try to send a value V to channel C2, and we bound that event to EVT1. Now, the high priority thread sync on a send event, try to send that EVT1 to C1, channel 1. And once the high priority thread sync on the send event, it blocked, right? And we got a chance to switch to the low priority thread. Let's assume we switch to this low priority thread, and the low priority thread try to sync on a receive event from C1, and since this receive event from C1 is a pair with this send event, we can pair this send and receive together. As a result, the EVT1 will be sending from high priority thread to this low priority thread, and we store that EVT1 as a EVT2 in this low priority thread. After this communication, the high priority thread will be allowed to resume to be up and run again, and it executes until it performs some blocking action. For example, it can be doing an IO. For some reason, it performs a blocking IO, and now we have a chance to switch to a low priority thread. And let's consider the low priority thread sync on EVT2, and now we have another chance to switch back to a high priority thread. And when it sync on EBT1, the high priority thread gets blocked again. Now the only thread left here is a low priority thread at the bottom, so we get a chance to switch to the low priority thread, and it's sync on the receive event from C2. So now we have two pairs of the communication. The first pair is this C1 here, received from C2 here, can be paired with the EBT1, since the EBT1 is communicating through C2. So this is the first pair, the EBT1 with this receive event. The second pair is the EBT2 with this receive event. And the question here is, which send should the receive to be paired with? And we want to consider the priority. However, there are different options. Should we have the event inherited priority from creation? If that's so, this EBT2 was created under the context of high priority thread. Right? And so the EBT2 should be inherited that high priority. As a result, this is a high priority, this is a high priority event. However, this EBT2 gets synchronized before EBT1. As a result, we should be pairing with the low part, this EBT2 with this receive event. And another option is, should the event priority inherit from the synchronization? If we look at EBT1, the thread that synchronizes on this EBT1 is a high priority thread. As a result, we should consider, if we consider the inherited priority from the synchronization, the EBT1 should be high priority. And the EBT2, the thread synchronized on EBT2 is a low priority thread, so it's a low priority synchronization. And as a result, we should be pairing with the high priority event. So we should be pairing with the EBT1 here. Now we have different options. So these are the options and questions we need to tackle when we consider the priority in the message passing. And things get more complicated when we consider a selective communication. A selective communication is a primitive that message passing model can provide. A thread can synchronize on a set of potentially available events. And CML provide a primitive called choose. You can choose a set of events from EBT1 to EBT2 up until EBTN. And CML will pick one of the event non-deterministic. And if none of the events are available, the thread that synchronized on this set of events gets blocked. And that's how the selective communication goes. And let's see how the priority plays when we consider a selective communication. And we have another example. This example has three threads, have a high and medium and low priority thread. At the beginning, we have high priority thread sync on a send event, and it send a value v1 to c1. Then high priority thread blocked, we switch to medium priority thread. The medium priority thread sync on another send event. It's sending a v2 to channel c2. And medium priority thread blocked. Now we move on to the low priority thread. Let's consider the low priority thread performs a choose. You try to choose between two receive events. So it can either pick receive event from C1, or it can pick receive event from C2. Both events are available because this event, this receive event from C1 can be paired with this thread, high priority thread, and this receive event can be paired with this medium priority thread. So since both of them are available, we can pick either one of them. And when we considering the decision, we want to know following factors. First, we want to know the priority of the thread that performs the synchronization, and we also want to know the priority of the events that is synchronized on, and we also want to consider the priority of the choose pools, events in choose pools, and if we don't consider all of these events, which is the mail currently doing, and it will try to pick either one of them non-deterministically. And if the CML pick the receive event from C2, then we are going to have we're going to unblock the medium priority thread. It's going to have the medium priority thread up and running. As a result, the high priority thread will never have a chance to pick again, and it's not going to making more progress after this communication. So this decision introduced a priority inversion, and we don't want that to happen. So this is something we also want to prevent. We want to consider when we introduce our priority schemes. So our schemes want to integrate both thread priority and event priority. This scheme to have rules about how the priority to be composed and to be compared. Our solution is a tiered priority scheme, and both events and threads are prioritized entities. Thread priority uses to prioritize computation, and event priority used to prioritize events in a selective communication. The goal of event priority is to give a final control over the priority between the threads of equal priority. And the important part of this tiered priority scheme is thread priority are given preference over event priority. So after we introduce this scheme, let's consider the example we have in our last slide. If we consider the thread priority, the decision, if we made a decision by a thread priority, then we know that this pair with the C1 is synchronized by a high priority thread, and the second pair synchronized the thread synchronized on this send event is the medium priority thread. As a result, if we want to make the decision by the thread priority, we should pick the first pair. As a result, high priority thread get a chance to unblocked and will resume and up and running again. There's no priority inversion in this case. And next, let's consider to boost up a medium priority thread to the high priority thread. Now, since both threads have the same priority, we want to make the decision by event priority. We have a primitive called send evtp, and this p will take a priority the priority is integer, the larger the number is, the higher the priority are. And we can see this set event has a priority 10, and this has a 5. 10 is greater than 5, so we will be pairing the first pair. So we will be paired after we pick up the first pair, the high priority thread on the top gets unblocked, and it's up running again. So this is the example applying our tiered priority scheme. And this tiered priority scheme gives us a power to express non-blocking synchronization, also known as polling. CML has no way to express polling. Consider the following code snippets. Here we have a polling function taking a channel, and it performs a choose between always event and receive event. Note that always event is to ensure the synchronization never blocked, and the choose in CML is non-deterministic. As a result, the CML may pick always event even if the receive event is available. And to perfectly behave as a polling function, we should pick the receive event whenever it is available. So in the CML, we can leverage event priority to achieve the behavior of polling by setting the priority of always event to the lowest possible. For example, to -1, and as a result, choose only pick always event when there's no other events available. And our system has a fully formalized semantics. In this semantics, we have an oracle. This oracle has a power to pick the correct pair in a communication. And we implement this semantics in PowerCML. Then we perform some case studies. Let's see a case study in a termination in Swerve. Swerve is a web server. It's entirely written in CML, and the current issue in the Swerve is that it cannot guarantee the shutdown gracefully. And the reason is the Swerve has to pick between the shutdown event or accepting new connections. And so if the shutdown event gets issued, it might not be picked when there's available connections. As a result, shutdown gets delayed. We can add priority to shutdown events. The change is only 3 lines of code. After we adding the priority to shutdown event, we can see that as the number of clients goes up, the broken connection, which was introduced by the shutdown delays, stays consistent under prior CML, while in the original CML, we have more broken connections. Under the heavy load, with 64 clients, we have 15 broken connections. And the next case study is a GUI shutdown protocol. We evaluate the response time of a shutdown protocol under the context of Xing. And Xing is a GUI toolkit in CML. We want to wait for all the widget to close up upon receiving a shutdown request. And since the choice has a non-deterministic selection, it will degenerate the response time because it will overlook a shutdown request. And the result is shown as a graph. These graphs, on the top, we have the result from CML. On the bottom, we have the result from prior CML. We can see the response time is significantly faster in the prior CML. The maximum of the shutdown time has been reduced from 100 seconds to 40 seconds. And moreover, there the variant of the shutdown time is more far less than the CML. So these are only, we conduct this experiment by only adding a priority to the shutdown event when we have achieved this benefit. Now, let's move on to a conclusion. Prior CML is an extension to the concurrent ML that introduced the priority to asynchronous message passing. Our next goal is to integrate prior CML on top of RT Milton. It's a compiler extension for real-time system from Milton. And so this is our today's talk. I'm happy to be here. Any questions?
Okay, many thanks. And a virtual clap to thank the speaker. And if there are any questions, please just unmute your microphone or raise your hand or do anything to catch my attention. And if everyone is shy, yeah, please, Dominic.
This is really nice. It seems to work super well. I really like the evaluation of this. I was wondering if you'd looked at trying to formalize this in any way, like some kind of pi calculus with priorities, or kind of give some sort of study the formal properties of this kind of thing.
Yeah, we are currently have a formal semantics, and it's based on cooperative scheduling semantics, and we were mostly done with the semantics, and we have a proof of the priority inversion with that semantics. So yeah, so basically our next step is try to get it done and get it published. It's basically our next steps. And as I've seen, we have those semantics in our slides. It's there, and we have the oracle that can pick up the correct communication pairs in the system. And yeah, so basically we have them in our CML, prior CML. Yeah.
Great. Okay. Well, we'll look out for the follow-up formal paper then. Yeah. Super. Great. Thank you.
No problem.
Any other question from the audience? If not, I think I can ask something. So you showed two test case, let's say, or use case, and they concern about shutdown processes. Can you do some other example where these priorities find a natural application? I don't know, maybe distinction between background and foreground processes or something like this?
Yes, we actually have some other benchmark, but due to the space and time limitation, we didn't present it. The other experiment we have tried and done with is like a web load balancer, and we basically try to balance between different servers with their current loading, and the capacity can be a sort of a priority. If so if an instance of web server has a lower load, they can be synchronized on higher priority, so they get more loading flows to the low load instance of web server. So that's another benchmark we have done in our prior CML.
Well, if there are no other questions, I have another, so I will take the opportunity. Okay. So you mentioned that you want to somehow to import Prio CML in the other language of your. from PADL of the previous, of 2 years ago. So I'm wondering, is that tool written also in CML, or is it in a different language? And if they are different languages, how difficult is to import the idea in another concurrent programming language?
Currently, there's no other implementation besides CML. And besides CML, we are implementing this tiered scheme. So my idea is maybe there is no huge obstacle that I can foresee to implement the geography in other concurrent languages, because mainly we implement we only change the channel structure. The main target is to cooperating with the channel structure and try to pair them, and we have some priority queues, and those implement details are discussed in a paper, detailed. And so I believe with those channel change, we can carry this idea to the other concurrent languages.
Okay, so it's not too, let's say, too binded to CML, so it can be
it can be adapted to other concurrent languages.
Okay, so many thanks for also this question session, and I will thank you again as a virtual clap for you and your colleagues. And I think we can move to the next talk. So let me take my notes. Now I'm moving between two windows and 4 windows, and it's a bit messing. So the next talk is titled
Hi everybody, my name is Bhargav Shivkumar.
Putting gradual types to work, and the speech is given by Bhargav Shivkumar. So please proceed.
And I'm going to be talking today about how we use gradual types in a language used to specify derivative contracts at Bloomberg. So let me start off by talking about what a derivative contract is. So a derivative contract is a type of a financial contract, and very informally speaking, a financial contract is an agreement that two parties participating in a financial market enter. And a derivative contract is a type of financial contract that derives its value from an underlying asset or a group of assets. When I say an underlying asset, what I mean is something like an equity, an interest rate, foreign exchange, and so on. Now, there are many types of derivative contracts, and a forward contract is an example of such a derivative contract. What a forward contract is that it's a commitment to exchange an underlying asset for a fixed price and on a future date. So, for example, you want to buy euro and you want to pay for it in US dollar at some point in the future, and you want to protect yourself from any market fluctuations in the forex value. You would enter into a forward contract wherein you can do this transaction. You can exchange your USD for euro at a fixed price at a particular date in the future. Now, another type of a derivative contract is a swap, wherein you make a commitment to do multiple such exchanges of the underlying asset over a period of time. There are many more types of derivative contracts like options, Himalayans, Phoenix Notes, and so on. But for the purpose of this talk, it would suffice to understand what a forward and a swap is. So at Bloomberg, we have this Bloomberg contract language, BCL for short, to describe such contracts. And to give you a very brief introduction to BCL, BCL is a statically typed language with Hindley-Milner style type inference, and it supports an extensive feature set and an extensive type system. And it was inspired by a paper by Simon Peyton-Jones and others, which talks about a programmatic way of expressing contracts and composing such contracts as well. So this example over here describes a forward contract which exchanges underlying forex, and it starts out by declaring some components of the contracts, like the date on which the contract is to be executed, the amount, the currencies being exchanged, and so on. So when you're writing such a contract, you would typically use some combinators or primitives to help you write such contracts, like the date function, which converts a string to a date type, or the current FX rate primitive, which converts, retrieves the current forex value at that particular point in time. And the whole point of this piece of code is to define a contract, and it's these two lines here which do exactly just that. So you have the receive and give primitive, which are used to create contracts, which perform the whole operation of exchanging your forexes. Both these contracts need to be acquired on the date, which is specified by the variable t, and your AND combinator ensures that both these contracts are acquired. So this is typically how end users or users of BCL would utilize BCL to write contracts and specify them programmatically. Now, while designing BCL, we were in a little bit of a design tug of war, and we were thinking about whether we should be, go with static typing or should we go with dynamic typing. And typically in such situations, language designers tend to pick a typing paradigm either based on users of that language or applications that is going to be built with that language or various other criteria. We too have had a little bit of a back and forth what we should use, and we recognized that static typing is definitely beneficial for us because of the correctness being an important criteria in contracts. And what I mean by that is it is important for us to catch errors earlier on in the contract definition process than later on. But on the other hand, this is a commercial language, and we would want to make sure that we cater to a larger user base. So we would want to make the language as flexible as possible so that many more people can adopt this language. So we were left to this question as to, given such varying interests, who do we appease? So to put this dilemma into a little more context, let me talk a little bit about the types of users who use BCL. So we have one type of user who we call as end users, who are typically finance professionals, and they have some sort of experience in dynamic languages like MATLAB and Python and so on. And our end users are concerned with development speed. So all they want to do is they want to be able to code contracts quickly, and then they can analyze the contract behavior. And for this particular reason, they like the flexibility that's offered by dynamic languages. So definitely dynamic typing helps them achieve this goal. A point I would like to note over here is this whole notion of flexibility is very subjective. So some users may feel that any amount of static type checking is inflexible. On the other hand, we have maintainers. Maintainers are software engineers with extensive experience in statically typed languages like OCaml, C++, and so on. Their main job is to implement language extensions, standard library functions, and they're also tasked with the responsibility to maintain backwards compatibility as BCL evolves. And so their primary concern is ensuring correctness of any standard library functions they provide, or ensuring that when the language evolves, it doesn't introduce any new errors. Static typing alleviates their pain by catching any bugs much before, and they don't percolate down to the end user. So we're back to this question as to how do we give both these types of users what they need. And if we were to put a little thought into it, what we ideally need in this situation is a statically typed language that feels roughly dynamic. One way to achieve that is to provide type inference. Now, type inference is a very nice way for you to avoid explicitly annotating your program with its types, and it gives the user a feel of a very dynamically typed language. But the fact remains that under the hood, everything is still statically type checked. So you are going to possibly end up with static type errors. And as I mentioned earlier, that you're going to have users who are going to feel any amount of static checking is not being flexible enough. So we would want to provide our users with a way in which they can actually defer this whole type checking process to runtime. And this is where we feel gradual typing definitely fits the bill. So gradual typing has ideally been used in such situations where you want to provide a middle ground for users who want to experiment with both static as well as dynamic typing. But what it provides for us is that we can now have coexisting static and dynamic code. And also, static code is not going to be blamed for any runtime type errors. So this provides a really nice bifurcation in which our end users and maintainers can code in BCL and be comfortable with how they write their code. So, of course, gradual type seems to fit the bill to solve the problem that we have. But how do we go about incorporating this into BCL? And in order to answer that question, I think a good way to work that out is to look to how other people have done it for inspiration. So we identified three main components for introducing gradual types into a language. So first, you're going to need the ability to annotate your terms so that you can differentiate between what is inferred and what is explicitly dynamic. Second, you're going to need to add this dynamic type to your list of existing types. And third, you're going to need an algorithm to unify your dynamic types with other types and type variables. So if you notice, I'm talking about unification of types and type variables because I'm approaching this incorporation of gradual types from the perspective of a statically typed language with type inference. So this gives me actually a nice way to broadly classify the different approaches that languages utilize when they want to, embark on such an endeavor. So there seems to be a static first approach where you start off with a statically typed base language and you add more and more dynamic type checking. And on the other hand, you have a dynamic first approach where you start off with a dynamic base language and you add more and more static type checking. Examples of languages that were developed with a dynamic first approach is you have languages like TypeScript, TypeTracket, Hack, variants of Python, Clojure, etc. And on the other hand, with the static first approach, it's an observation that there seem to be lesser mainstream static languages that introduce this notion of gradual types as defined by Seek and Taha. Of course, they have some support for dynamic types. For example, C# and Java introduce a dynamic type and they have a way to perform some sort of runtime inspection on it using reflection, very similar to what Abadi and others have proposed. And on the other hand, you have languages like SML, OCaml, and Haskell, which again don't support gradual types, but do support some form of dynamic typing, either through GADTs or type classes and so on. But all of these are not as seamless as how gradual types would be for our situation. There is also a small section of work out there which addresses this whole issue of gradual type inference. So they start off with a static base language and they look at how you can add dynamic types into this whole type inference process. And those two works are two important works in this bucket. Basically would be one by Seek and Vajrajani and the other by Garcia and Simini, which addresses the same problem, albeit from slightly different approaches. So what we want for BCL is an approach that fits into BCL. What we want to be able to do is we want to be able to infer static types and explicitly annotate dynamic types. So what I mean by that is, let's say I have this increment function as defined over here, and I annotate the increment function with the type dynamic to int. What I want to be able to do is I want to statically infer the type of, let's say, x in the body of increment, or even the return type of the increment function. And I want to be able to dynamically check the argument that is passed to the increment function. So if you see this, at some point, this kind of involves exploring how this dynamic type is going to unify or interact with all these various types that's being inferred. So as I mentioned earlier, BCL has a Hindley-Milner style type inference, and we use Hewitt's unification algorithm. And now we're trying to incorporate the gradually typed lambda calculus. And whenever you have to incorporate gradual types into your language, you have to deal with this notion of consistency, or the relation consistency between types. But unfortunately for us, consistency really doesn't describe how dynamic types would be related to type variables, because type variables are an aspect of a language that performs some sort of type inference. But Seek and Vajrajani have already studied a similar approach, and they come up with this consistent equal relation, which deals with how dynamic types can play well with type variables. Now, we can't use this approach wholesale, but we can definitely draw inspiration from it. So we can try to introduce this notion of consistent equal relation into our own type inference algorithm. And of course, it follows that we would have to expand this out to make sure that this relation can support more complex types like recursive types or structural composite types and so on. So in this way, we were able to incorporate gradual types into BCL, and we go into depths of our implementation in the paper. But all this is going to be a moot point if we are not able to bridge the gap between our end users and maintainers. So let's see, with the help of examples, if gradual type really lets us achieve our main goals. So we wanted to provide our end users with flexibility by introducing gradual types. And let's see if that's possible with this example. So we saw the forward contract defined earlier on. This is the same forward contract, just I've just made that out into a function. I've named it fx forward. And now this function takes the date, currencies being exchanged, the amount, and so on as arguments to that function. This little piece of code over here is the swap contract, which I, again, initially explained what it does. And a swap contract, to recollect, is basically a contract that does multiple exchanges over a period of time. And if you were to think about this programmatically, it literally translates to mapping this forward over a series of, or a list of dates, because all the swap is a series of forwards. Now, at this point, I'd like to mention that this is a very nice way in which you can compose contracts. So you can use smaller contracts to build much more bigger and complicated contracts, which is an advantage of expressing contracts programmatically in a language like PCL. So our end users typically would perform such a task, and they would build much more complicated contracts by using many smaller contracts as subcontracts. So if our end user were to go ahead and execute this in BCL, they're going to be hit with a type error, and this is going to be a static type error. The error is going to say, hey, fx forward expects a date, but it got a string instead. And this is a very valid error, because if you were to see, the fx forward function expects a date type, but at the point in which fx forward is called, it is mapped over a list of strings. So the ideal way in which our end user needs to address this would be to use something like the date primitive we saw to convert this list of strings into a list of dates. But it can so happen that our end user at this particular point of time only wants to input this contract into our system to study the way in which various subcontracts behave or interact with each other. And at this point of time, the exact dates on which the contracts are going to be executed might be irrelevant for them. So they would want a way in which they can, bypass this static type system to be able to analyze the contract behavior. And this is exactly what gradual types gives them. So with gradual types, I could, annotate this list of strings as a list of dynamic types, and the static type system is not going to complain anymore about this type mismatch that occurs. And the end user can go ahead and try to analyze the behavior of various parts of the contract. Now, if the end user doesn't address this issue in the future, they are, of course, going to encounter a runtime type error when they execute the contract. But at least now they're aware of existence of such a thing, and it's up to the end user to address it at the appropriate point of time. So clearly, gradual type provides an escape hatch for end users who feel very constrained by the static type system. All right, so what about our maintainers? Do they get anything? So our maintainers are really happy with being able to use static typing and ensuring that whatever code they write is ensured to be free of any type errors. But they can also use gradual type to enhance our end user experience and give them some tools to better express contracts or better write code, whatever they're writing. So there is a nice use of contracts as templates in Bloomberg. So what happens is templates are written by end users who have a particular expertise in derivative contracts. They could be somebody who has a better understanding of the markets or a better understanding of how to write such contracts. So these templates are basically functions that produce contracts, and they're stored in a database. And any other end user who wants to use these templates can do so through a UI and can instantiate these contracts by providing arguments through that UI. Now, it would definitely be beneficial if these templates can be used in BCL code. And this is exactly what the maintainers can provide through a load template primitive. So the load template primitive can be used to load these templates which are stored in the database into your contract code. So for example, if my forward contract was a template, I can load that template into my code and then use it in a swap contract, just as I did previously. But this follows that the load template needs to return a dynamic type, because your templates could return various types, and you want to use the same primitive to load any kind of template. So not just the subcontracts, you can also use these loaded templates for maybe performing some sort of a minor change in the code. So like, for example, if you want to load the forward contract and put some limits on it or cancel it when it hits some conditions, this sort of primitive helps make any such additions or evolutions to your code. So of course, now maintainers have a way in which they can enhance the end user experience, and our end users also have something to take away, because now they have a new way in which they can utilize the templates that are present in our system. Now, we have kind of achieved our main goal of providing this common ground for our end users and maintainers to use BCL, but gradual type seems to be a gift that keeps on giving. So we get a lot of add-on benefits by adding gradual types, which was not our original intention for adding gradual types, but it's still something that we can use. An example for such a thing is that we can now do some sort of ad hoc polymorphism. So let's say I want to define a contract wherein I receive an amount in dollars equal to the noon temperature in NYC. And I can go about doing that using the scale combinator. So what the scale combinator would do is it would take this time varying value, which is the noon temperature in New York City, and it would multiply all the payments in the contract by this time varying value. So if you were to think about this very intuitively, this seems like it can be very much more simplistically handled by the multiplication operator. So this is exactly what we can do with the gradual types help. We can make sure that we can use the multiplication operator for this for defining this contract, and then the multiplication operator would resolve it to the appropriate combinator when the types are resolved at runtime. Now, of course, it follows that we now would need a way to inspect types at runtime, and more than a disadvantage, this sort of a function would be a very good advantage, and it would help us provide some more features that can help enhance how users write code. For example, if we have a runtime inspection ability, we can write some Python-esque type conversion functions. For example, an any to string function, which would take any argument, convert it to string, or an any to date function, which would take an argument of any type and convert it to a date. So apart from these, sort of advantages, there is an added advantage that we get, which is not just as a result of adding dynamic types, but also as a result of doing it so in a static first approach. So in compilers, often they can do some sort of optimizations with the help of static type information. Now, in a dynamic language with gradual types, any unannotated types are implicitly dynamic. And for a user of such a language to leverage these static optimizations, they would then need to go ahead and annotate their entire program. But with BCL, unannotated types are implicitly static. So our users don't miss out on these optimizations, and they don't have to go through the effort of having to annotate their entire program. So we can say that gradual types definitely makes not just life easier for our users, it definitely gives us a lot more value-added benefits to make sure BCL is a much more extensive language. So I would like to conclude this talk by talking about where we want to go with this whole work. So it is our general observation that dynamic typing seems to be preferred by a lot of users, especially those with a without a computer science background. And on the other hand, static typing is very essential in ensuring correctness in domains where correctness is important. Gradual typing gives a very good middle ground, and it's something that literature should explore to make sure that we can identify various innovative uses of it. So to further discuss, we intend to gather feedback on how our users and maintainers use gradual types. And we believe that we would be able to get new and novel ways in which we can apply gradual types to the whole domain of financial contracts. And we would like to come up with a more detailed paper armed with such a data as to how gradual types are being modified and used by our users, and even come up with various other applications of gradual types in our domain as well. So thank you all for your time, and please let me know if you have any questions.
Okay, many thanks for your talk. And if there are questions, as usual, please unmute your microphone or raise your hand. Manuel, please.
Hi, this is Manuel Hermenegildo. Very nice talk and very nice overview of advantages of gradual typing, which I totally agree with. Just to provide a pointer, since you didn't mention, a pointer to the work done in the area of logic and constrained programming languages, where in particular the work of the Chao language, the Chao prologue language, which I would argue is the first language to have these characteristics of gradual typing and so on. So anyway, just a pointer to that. Like I said, I think it was the first. It does have all these characteristics of combining the static and the dynamic aspects of languages, checking things statically. If you don't check them statically, kind of manage to check them statically, then you generate runtime tests. You can do, call your properties at runtime, to check and switch between implementations. The polymorphic. The polymorphism that you have talked about. Anyway, just a pointer to that work, which in case you haven't seen it.
Yeah, absolutely. I mean, that's a very valid point. I think there are a lot of languages, like ones that I failed to mention, like Chao, which do a lot of such gradual typing or incorporating dynamic types in some new and novel way for different purposes. And that's why I think that it's important that we also explore ways in which gradual types would benefit a whole lot of people out there. So
yeah, I think it's very important to underline that these are great ideas. This is great. It's just the way to go. Yeah,
absolutely.
Yeah, Chao is not novel, by the way. It's relatively old. I mean, okay.
Yeah, somehow it combines the formality of the static type checking with the, let's say, more flexible approach of dynamic typing.
Right.
So yeah, should be a win-win.
I would argue that we were the first ones to propose that. I mean, that's in the 90s.
Good.
And implement.
Can I say something? I also have some questions, but indeed, Chao. I think Chao goes from this dynamic first approach that you mentioned. I think it's a very nice classification. That language can be in either one side or the other, and then they try to converge.
Yeah, the best of both approach. Yeah.
I have one question. I think this is a very, very interesting work, but gradual typing. I mean, once you have dynamic types, then you have the possibility of runtime errors. Is it right? I mean, in your language now, if you have dynamic types, then it's possible that you write a contract that in the middle of an execution goes crazy. Or what is your experience with that? Is that a bad thing or a good thing? Because I think this thing that you mentioned, that variables by default are static in your language, I think it's a good idea, because it's what's your experience with that, with moving to a more dynamic thing?
Sure. So I guess, so if I understand your question correctly, you're asking how dynamic typing. I mean, what's our experience in how dynamic typing makes it better for our language. And I think the answer to that is the fact that it's more about giving the flexibility for our users in terms of how they want to write their code, whether they want to do some sort of rapid prototyping like in the example that we saw, or they would want to utilize the benefits of having a static type system, wherein in the whole contract description process, they kind of can choose to either make use of the static type system and better their code as they write it, or they could probably go ahead and describe a contract, because contracts in general can be very complicated. You have a lot of subcontracts, you have a lot of interactions between various subcontracts that you have. So I think it provides them a nice, the users a nice way in which they can go about thinking about how they structure their entire program or contract. And I think what gradual types, so again, so we do need some way of dynamic type checking. So that is a point, that was the initial point. And there are many ways to do it. Not all languages have this notion of gradual types as specified, like by Seek and Taha. There are other ways to incorporate some sort of dynamic checking. But I think that gradual types gives a nice way in which the guarantees are like encapsulate. So we know what we can expect from such a way of incorporating dynamic types into our language. So I think that is the advantage of using our this sort of approach to having dynamic types in a language as well. So does that answer your question?
More or less, but do you have dynamic types then in production code, or is it something more for prototyping and?
Oh no, we do have it. We do have it, as in it is exposed to our end users as well. So it's just giving them a way to specify it in different ways.
Well, I think it's a very nice approach. Yeah, thanks.
Yeah, if you had to express about in favor of one or the other, which one you will use, more static or dynamic, or maybe dynamic for quick and small code, and maybe static for code that you have to maintain longer?
Yeah, so again, it depends on the way in which I want to use BCL. I don't think it is based on how long the code is. I think it's based on how quickly I want to achieve my goals, or what my goals are in writing the contract. So as I explained, like the maintainers of BCL, they're typically tasked with writing all these, combinators, standard library functions, and all of them. And for them, static typing is very important because they don't want any bugs that they introduce to kind of percolate down to other users of the language. So and for our end users, it kind of is a matter of what they want to kind of achieve. So I guess the answer is really that it depends on what I want to do at that particular point of time. And having both these options is definitely good. Static and
the code of the end user is intended to be maintained, or it's one shot maybe?
I'm sorry, could you
repeat? The end user, the code that usually writes is to achieve a single task maybe, or it's going to be maintained and run another 100 times, I don't know.
Right, so it does achieve one specific purpose, of course. So contracts have like an expiration date of some sort. So at that particular point of time, this contract is going to expire at some point of time. So it is time bound, if in a matter of speaking, but it follows that there's a lot of things to do with how they specify them more than this aspect of how long that code is being run for. So yeah.
Okay. I think if there are no other questions, I will thank you in virtual clap. So we can move to the third talk. The title is Samati, DSL with flows.
Hello, my name is Reed Samati, a DSL
assets. And the speaker is Reed Hoey from Illinois. So please, let's proceed.
Flows for safe blockchain assets. So there are many uses for smart contracts on blockchains. Smart contracts are just programs that run on the blockchain, such as cryptocurrencies, voting, crowdfunding, auctions, and many others. Smart contracts manage and importantly lose a lot of money. The DAO contract lost over $40 million in 2016 due to a simple reentrancy bug. And there are many other examples of smart contracts losing money. And importantly, smart contracts on Ethereum cannot be patched after being deployed. meaning that if there's a bug like this, you may be able to just drain all of the money out of the contract without anybody being able to do anything. So this is one of the reasons that we're designing this new programming language called Semantic for writing smart contracts. It uses a new flow abstraction, which represents an atomic transfer operation. This operation is very common in smart contracts, so having the language is useful and convenient, but it also combines with other features that we'll discuss to make writing smart contracts safer. So the simplest kind of flow selects values from a source and sends them to a destination. So it looks like below, source, arrow, destination. Semantic also has features to mark types with modifiers, such as asset, which combine with flows, and another thing called type quantities that make some kinds of bugs impossible. So here we have a type declaration where we use two modifiers, fungible and asset, which we'll talk about more in detail later. And it's represented by UN256s, unsigned integers, which just represents how many tokens this value represents. So transformers in Semantic are play the role of functions or methods or procedures, etc. Transformers use parameters to transform some value. Typically, this is the last value in the argument list, but it could be any of them. The parameters are sort of auxiliary information that is used to perform this computation. So in this example, we have this transformer called transfer, which is meant to send some tokens from some account to some other account. So we have balances, which is a map from addresses to tokens. The any and the one, those are the type quantities. And what it means is that balances is a map that contains any number of key value pairs. That's what the first any means. The keys are a type 1 address, meaning that it's just an address value, just like a standard value in a programming language, standard programming language. And the values are type any token, meaning that they're token values that can have any value. So 0 to the max. Destination is one address, so again, just an address. And then amount is any UN256, so an unsigned integer of any value. And then the body on line 4 is a single flow. What we do is we look up the balance of the sender, we select amount tokens from that, and then we put it into the destination account's balance. So we could also rewrite line 4 to look like the below, so it looks more like the source arrow destination form. The version on line 4 is just syntactic sugar for this, which is sometimes nicer. So we look up in the balances, the sender's balance and select amount from that, and that's the source, and the destination is the balance of the destination account. Additionally, there's a more complicated form of flows called transformer flows that have a transformer call in them. And what they do is they select values from a source, they run the transformer on each one of these values, and then they send these transformed values to the destination. So as pictured below, source arrow transform, whatever the transformer is, then to the destination. The underscore represents the position in the argument list that the values from the source will be inserted into. In this case, there's only one argument, so it's just the one argument. But in the transfer example, we could put the underscore in different places depending on how we want to actually use transfer. So this transformer can either be a user-defined function like transfer, or it can be a constructor, which can create new values of name types. So if we recall our type declaration of token, then what we can do on line 2 is we create a new token value that has value 10, and we put it into a variable called myToken, and this is a transformer flow. Another important feature of flows is that they can fail if they're not valid, meaning that the selected values are not in the source or they cannot be sent to the destination. So failures are exceptions that can be caught, and if they're not caught, then the transaction reverts and no changes are made. So here we have an example in an auction where what we want to do is when a new bid is placed, if that bid's value is greater than the current highest bid, then we want to replace the highest bid. Otherwise, we want to refund the bid to the person who placed the bid because it's not higher than the highest bid. So we declare a new type called bid, which is a consumable asset. We'll talk about consumable later. It has some value represented by a token value of any possible value. We have a sender, which is just the person who placed the bid, represented by an address. And then we have this try catch block. So the first thing in the try block on line 7 is this only when. Essentially, it's a precondition, but it's implemented using the flow commented out on line 6. And if this flow fails, then what happens is the exception is thrown, and then it's caught, and we go to the catch block. But if it does succeed, Then on line 8, we refund the highest bid's value to whoever placed that bid, and then we destroy that bid because it no longer has any value, and then we replace it with the new bid that was placed. Otherwise, we refund the bid that was placed because it's not higher than the highest bid. Another important feature of Smouthy is type quantities. So type quantities are used to approximate the number of values in a variable. Primarily, this is to track asset variables that can be dropped. Specifically, if an asset variable is empty, then it can be dropped. Type quantities that we plan to support are empty, any, one, and non-empty, representing 0 values, any number of values, exactly 1 value, and at least 1 value, respectively. Type quantities are more or less an adaptation of linear types for containers that allows for some more precise analyses in some cases, some of which we'll see later. And they can often be inferred or just inserted with well-chosen defaults. So all the type quantities in the first example, we can actually omit. We don't need any of them. The default type quantities will give us exactly what we had. So you can write the somewhat simpler transformer definition shown below. And the last important feature of Smouthy is modifiers. So modifiers specify how variables of a type can be used. Currently planning to support 5, asset, consumable, unique, fungible, and immutable. So assets are values that must not be reused or accidentally lost. This is typically used for things like money or tokens, but it's also useful for things like bids in an auction or votes in an election or lottery tickets or anything that we don't want to accidentally lose or overwrite. This corresponds to linear typing with by default, or with the use of the consumable modifier, then affine typing. So consumable is an asset that may be disposed of. But it must be disposed of using this consume construct that we saw earlier, which documents that disposal is intentional. So you won't accidentally forget about it, you intentionally destroy it. For example, this is useful in this context of bids in an auction, because while we shouldn't lose bids that still have value during the auction, it may be safe to dispose of them after the auction ends, or if, like in our earlier example, a higher bid was placed. The next modifier is unique, which just means that values of this type can only be created once, and they must be immutable. This allows us to check just once when it's created that it hasn't been created before, and if that's the case, we know that it's unique. We also have fungible, which represents values that can be merged and are not unique. This is basically all currencies, dollars, euros, Bitcoin, Ether, etc., where it only matters how much of that currency you have, not sort of which pieces of it you have. So if you have $2 and $2, you have $4. You haven't lost any information by merging them together. And lastly, we have immutable, which are values that cannot be changed. So this following code is not legal. So we declare a new type called T, which is essentially just a wrapper around U256 that's now immutable. We create a new value of type T with underlying value 0, stored in a variable called little t. And we try and flow 57 to little t, and this was not okay because the type T is immutable. So using this more declarative flow-based approach gives us several advantages over imperative safe state updates, including safety guarantees, but also some other advantages. So statically, we can guarantee these things, such as that for assets, each flow will preserve the total amount of each asset type. So we won't lose or duplicate assets, except for flows that consume or explicitly allocate assets using new, but in that case, it's clear that they will they have the potential to change the number of assets. Immutable prevents values from changing, as discussed before, and that can be checked statically. And also we can use type quantities to allow us to distinguish some cases when we're guaranteed to have empty variables versus when we can't know ahead of time. So for example, in this line of code, we use a new construct that we call filter to select exactly one value from X such that P of that value holds, and then flow that to Y. So if X has, for example, type 1t, then after the flow, we know statically that X is type empty t now, if the flow succeeds. If the flow fails, then it throws the exception and is handled somewhere else. But after this line, it's safe to assume that X is type empty t, even though we didn't, for example, flow everything out of it. Because we have the type quantity, we know that it will be empty. There's also a number of dynamic safety guarantees that Smouthy can give us. So Smouthy will automatically insert dynamic checks of a flow's validity. So for example, if we're flowing money, a flow of money might fail if there's not enough money in the source or if there's too much in the destination. So for example, due to overflow, because U256 is only a finite max size. Or a flow of values from a multi-set might fail if the specified values are not found in the source. So for example, if we have a multi-set A and we select values X, Y, and Z, if X, Y, and Z are not all in A, then that flow will fail. And a flow of value might also fail if it would overwrite an asset in the destination. So for example, if we're replacing the highest bid by bid, if highest bid has type any bid, then we have to dynamically check that highest bid doesn't have any values, because if we were to flow there, it would overwrite the highest bid, therefore losing money because we're not keeping track of it anymore. But in some cases, this can be checked statically. So if highest bid has type one bid, then we know statically it will fail. And if highest bid has type empty bid, then we know statically that it will succeed. And we could, if we implement it this way, not even have that dynamic check. And lastly, the unique modifier is also checked dynamically. Whenever the values are created, we check that hasn't been created before, and that ensures the values will be unique. So as additional advantages, we hypothesize that flows will provide a clearer way of specifying how resources flow in the code itself, because the source and the destination and the various filters and transformations are all explicitly there. It's not the imperative approach of removing some values from a collection, maybe filtering through them, maybe transforming them, possibly putting them back, and then adding some values to the destination. It will be all there in one spot, which we hypothesize will be clear to developers. And for a similar reason, we can automatically generate these descriptive error messages, such as the one shown below, because we know what the source is, and we know what the destination is, and we know what was supposed to be selected. We don't just say underflow or overflow. We know, well, there weren't enough tokens to send here or something like that. So here's an example of using type quantities and modifiers to guarantee some correctness properties in a lottery. So in addition to sort of a basic correctness property of not losing lottery tickets, we also want to ensure that each user can have at most one ticket, that we can't end the lottery before somebody has won, because then whoever's running the lottery might decide that as soon as anybody plays and they know they're wrong, they'll just end the lottery, and that would be a lottery that you would not want to play in. And then we also want to make sure the jackpot is fully paid out, so no money gets trapped in the contract. This is a problem that happens in Ethereum fairly often. And so to do this, we create two new types: ticket owner, which is a unique immutable address, meaning that there will only be one ticket owner per address at most. And the ticket type, which is a consumable asset, because we don't want to lose tickets accidentally, but at the end of the lottery, we'll want to destroy all the tickets because perhaps we want to reset for a new lottery. So tickets have an owner, which is a ticket owner, which again ensures that these tickets will be only one per user. And they have a guess, which is whatever number they guess in the lottery. If they guess right, they win. And if they didn't guess right, then they lose. Now we're just showing this transformer to end the lottery. There would be other ones, of course, in real implementation. End the lottery has the multi-set of tickets, the balance, the total balance, the jackpot to be paid out, the owner of the lottery, and whatever the winning number was, selected in some way. So the first thing we do on line 11 is we get all of the winning tickets. And we do this on line 12 using a filter on the tickets set, selecting the non-empty multi-set of tickets such that they are winners. And this ensures one of our correctness properties, that we can't end the lottery before somebody has won, because if this filter doesn't select a non-empty multi-set, then this flow will fail and it's not caught, so this transform will fail as well. So the lottery can't be ended before somebody has won. And then after that, what we do is we want to pay each winner their fair share of the bounce. So we split the jackpot among each one of the winners fairly, and we use a transformer flow to essentially iterate over the multi-set of winners and pay them each their fair share. And we ignore the return value because pay in this formulation doesn't return anything, it just updates the balance. And finally, we send the rest of the balance to the lottery owner. So this is necessary because jackpot may not split among all the winners evenly. And in that case, we want to make sure that we don't lose money in the contract. So we have to do line 14. If we didn't have line 14, we would get an error message saying that balance has type any ether. It may not be empty. It has to be empty for us to be able to drop it. And then lastly, on line 15, we consume all the tickets because the lottery is over. And if we wanted to, for example, redo the lottery, then we could do that now or not. So this ensures all of our safety properties using both the type quantities, non-empty, and also to track that the balance still has assets in it, and also the modifier is unique, consumable, asset, immutable. Next, we want to compare Samathy to Solidity, because Solidity is the most commonly used smart contract language on the Ethereum blockchain by far. And Solidity doesn't have support for managing assets. It's a fairly standard imperative style language. So what we have is the type. We have this same declaration from before, declaring the type and the transformer transfer from Samathy. And then below is this equivalent code in Solidity. We declare a contract, which is essentially a class called ERC20. ERC20 is the standard that we're partially implementing. There's a field called balances, and then this transfer function, which again takes the address of where we're sending the tokens and the amount of tokens to send to that address. Transfer is implemented in these lines 4 to 6, first by checking that the balance is sufficiently large, then subtracting the amount of tokens to send from the sender's account, and then adding them to the destination account. So here we can see that the Samathy version is somewhat more concise because the body is only the single line, and that we also get the static benefits of Samathy checking our code to make sure we didn't accidentally lose assets somewhere. And that is something that Solidity doesn't have any support for. And now one more example to compare Solidity and Samathy, where we'll consider a slightly more complicated example with a simple voting contract that allows voters to vote on proposals. Only one vote per address is allowed, or one vote per user. Users are represented by addresses, and then whichever proposal at the end has the most votes wins. So again, we have Samathy code on top and Solidity code on the bottom. So in Samathy, we declare a type of voters as unique immutable asset addresses. This means that there will be at most one voter per address, and they're assets because we don't want to lose any of the voters. Similarly, for proposal names, we don't want to have two proposals with the same name because then it would be unclear what you're even voting for. And then we declare a type of election to keep track of the whole thing. So we have a chairperson who manages the election, a multi-set of voters called eligible voters, which is in fact a set because voters are unique. Eligible voters is the set of people who are allowed to vote but have not yet voted. And lastly, we have this map of proposals, which maps proposal names to sets of voters, the set of voters that voted for that proposal. Then the Solidity version, we have this contract wrapping the whole thing, where we have a voter struct storing information about the voters. First, their weight, which we use to track whether or not they've been given the right to vote, voted, which tracks whether or not they voted, and vote, which is which proposal they voted for. And then we also have the proposals, which have a name and how many people voted for them. If we have the chairperson, we have a mapping from addresses to voter information. And lastly, we have the array of proposals. We're going to talk about two basic transformers that are sort of the basis of the selection system. One is give right to vote, which allows people to vote. And then the second is vote, which does the actual voting. So first we'll talk about give right to vote. So here we again have on top the Samathy code, and below we have the Solidity code. So in the Samathy code, we first use only when to make sure that the person calling this transformer is the chairperson, because not anybody is allowed to give people the right to vote, only the chairperson. Then we create a new voter with whatever address and put that into the set of eligible voters. So because voter is a unique type, this ensures that the person has not voted before and that they haven't been given the right to vote before. Then below, in the Solidity version, we again check that the sender is the chairperson. And then we check that the voter has not voted. Then we check that the voter has not been given the right to vote by checking that the weight is 0. And then we give them the right to vote by assigning weight to be 1. And then for the vote transformer / function, we have in the Samathy version, this flow on line 2 that implements the whole thing. We take the sender out of the set of eligible voters and put them into the set of people who voted for the specified proposal. So if they're not in the set of eligible voters, either because they haven't been given the right to vote or because they already voted, this will fail, but otherwise it will complete the voting process for that person. The Solidity version does a similar thing where we first look up the voter. We make sure they haven't, that they have the right to vote, that they haven't yet voted. Then we mark that they have voted, we mark what they voted for, and then we add them to the corresponding proposal vote count. So we can see several things from these examples. One of them is that Samathy is suited to a range of applications. We talked about originally tokens, but also lotteries, auctions, bids, lotteries, and now voting. So additionally, as in this ERC20 example that we started out with the tokens, the Semantic implementation of this voting contract is more concise than the Solidity implementation. And we also see using modifiers both to enforce dynamically, such as unique, that certain correctness properties are fulfilled, but also using modifiers such as asset, we can ensure statically that there are none of these accidental asset loss problems. So in the future, we hope to fully implement Semantic by compiling it to Solidity, because that's an easy target platform for our purposes. We also want to prove the safety properties of the language, such as assets not being accidentally lost, immutable values not being changed, unique values actually being unique, and so on, and also basic type safety. And then we want to study the benefits and costs of using this language via more in-depth methods, such as case studies, performance evaluation, and possibly studying the application of flows to other domains, either other blockchain platforms or even other programming languages. So in conclusion, we've presented the Semantic language for writing safer smart contracts. Semantic uses our new flow abstraction, assets, modifiers, and type quantities to provide safety guarantees for smart contracts. Statically, we can guarantee that the assets will not be accidentally lost or duplicated, that immutable values won't change, that consumable assets can be consumed only if we use a consume construct on them. And dynamically, we can ensure that the flows are valid, meaning that we can both select the values we want to select and that we can send those values to the destination. And we can also check the unique modifier. And we also showed 2 examples of smart contracts in both Solidity and Semantic, showing that Semantic is capable of expressing smart contract functionality in a concise manner, but also retains the safety properties that we want when we're writing smart contracts. Thank you.
Good, many thanks. So if anyone has question, please turn on your microphone and ask. No one?
I have a question.
Good, please, 2 questions.
Go on, Jose.
Thank you. Mine is simple. Will it be possible to target other languages than Solidity? Or I'm not very familiar with this. Solidity runs on Ethereum, but right?
Yes.
Will it be possible to target multiple blockchain languages like Tethos or whatever?
I don't see a reason why it wouldn't work, but I haven't really looked into it. We're focused on Ethereum just because it's sort of one of the more popular ones.
Okay.
So this could be like maybe what is Keras in the machine learning. Okay, so some more general language that then relies on some lower level language. So I don't know, maybe you can compile not just in Solidity, but in some other language for some other blockchain stuff.
Yeah.
Yeah, good. So Dominic?
Yeah, so I thought it was interesting the way you sort of talked about them being like linear types and affine types, and this sort of made a lot of sense in this context. I seem to remember there was some work that was kind of related to this, I think, based on some sort of session types like thing. Ankush Das, Stephanie Balzer, and a few others. Are you aware of that? I think it was called Nomos or something like that.
Yeah, I'm vaguely familiar. I've heard of it, but I haven't read the paper in depth or anything.
Okay, all right, well, fine. I just thought they seem to be something there as well, sort of saying, doing something similar with linear type like things to capture something. So
it also reminds me of linear logic, where you can consume a token only once and then.
Yeah, I mean, it makes a lot of sense to treat these, resources like money in this way, right? And
yeah, there's a lot of the new blockchain languages people are proposing use linear types or something like it to manage the assets. This approach is supposed to be sort of, like a nice abstraction for working with these things, nicer than some of these other languages. But it's also, yeah, as I mentioned, like slightly differently adapted because the type quantities aren't exactly linear types. They let you do some of these other nice things, which I found to be useful.
So there also seemed to be something that was, you were saying about the containers, was that to do with the number of things in the container?
Yeah.
A bit like an index type, a slightly sort of abstract index type.
Yeah, it's just, yeah, they're sort of like approximating how many elements are in the container. As opposed to just, you know, I have a thing and then I use everything or I don't use it. Like, you know, with linear types, you can say, you know, I use some part of it.
Yeah. Yeah, so there might be some kind of more fine-grained sort of properties going on there than what linear types would normally give you. Yeah, nice. That's interesting. Yeah,
good. So maybe I take the opportunity to do another question. So at some point there was some line of code that was required, the keyword required, and then was comparing two arguments. So is this part of the dynamic typing of Solidity, or it's just like an answer to what?
Oh yeah, the require statement Solidity is just yeah, it's a runtime check. So when the code runs, it checks, and if it doesn't pass, then it fails.
This doesn't become part of the type of anything, right? So
no.
Okay, yeah. And also maybe, so when you're going to implement this, so how can you implement this? The idea is to do some kind of transpiler that will go from your language to Solidity, and then you are going to interpret with Solidity.
Yeah, so
the transpiler you can implement in any language, or you must rely again on something related to Ethereum.
No, any language is fine. It's currently in progress. So right now it's written in Haskell, but that's not a requirement. It's just
okay. So your choice will be Haskell. Okay, very good. So I think if there are no other questions, I thank the speaker again virtually. And before giving the word to Dominic and Jose, I thank both of you for organizing the workshop and for taking care of everything with simplicity and making the job of reviewers and authors as easier as possible. So many thanks to both of you for organizing.
Thank you to you, Mario. And also, this was the final session and the end of PADL. We hope you enjoyed PADL this year, despite that it is a virtual event. And well, Dominic, I think we have to thank all the authors, PC members, organization in POPL, the fantastic Causal support that's fixed all the technical issues the last minute.
Yeah.
The student volunteers, the session chairs, and the invited speakers. And do you have something else to add, Dominic?
No, I think that's great. Yeah, it's been a team effort. We've had lots of people involved in helping us out. So thank you to them all. And the proceedings is linked from the website for the next 4 weeks there, open there. So yeah. So
let's hope that the next PADL is not a virtual one.
Yeah. Yes, it'd be great to be all together again. Yeah.
Okay, so thank
great.
you.
Well, thanks very much, everyone. See you soon. We'll be around at POPL. I'll be around for the rest of the week. Yeah. Okay. Bye.
Bye. Thank you.
Bye. Goodbye.